So to start off with, we need to review a little bit of vocabulary. Remember that an aqueous solution means that the compounds are dissolved in water. Solute is what is being dissolved, and the solvent is the dissolver. Molecular solutes, this is a covalent compound that exists as molecules in solution. This is the dissolution that we talked about last time, where we have our covalent compound and it goes from a solid to an aqueous when dissolved, but it is dissolved whole. And then ionic solutes, they undergo dissociation. So they dissociate in solution, the ions are going to separate, and the individual ions, both the cations and the anions, are what exist in solution. So again, this is dissociation. Ionic solutes is what we're going to mainly be focusing on with our types of reactions in aqueous solutions. So what happens when two aqueous solutions are combined? When we talked about dissociation and dissolution, we only talked about one ionic compound that was dissolved into water. So now we're going to take two solutions and combine them. So the solutions, remember, they contain particles, and those particles are in the form of ions. And the individual ions are going to react with one another. This is typically going to be a double replacement reaction that is going to occur. And we have three types of products that can form. The first is a precipitate. And remember, this is a solid, or it is insoluble. Water, which we discussed in our chemical reactions unit, is going to be a liquid. And gas, we would label with gas. So let's take a look at the three different products and how they form. So our first is reactions that form precipitates. The dissociated ions react to form an insoluble compound. That insoluble compound is the solid that is formed, and that is called a precipitate. So you can see evidence of this in the reaction. These are called precipitation reactions because they produce a precipitate. Now, we label them as a solid, but precipitates actually have a gel-like consistency. And the reason being for that is there's still some water attached to it. We can dry it out and it would be more of a solid that you are used to. We determine the product formed using the solubility rules. Soluble will dissolve, so that's going to be labeled aqueous. Insoluble will not dissolve, so that would be a solid. And then we can also occasionally have a slightly soluble where a little of it would dissolve. Reactions that form water, these are called acid-base reactions. The dissociated hydrogen ion from the acid and the hydroxide ion from the base are present in our reaction container, and they combine to form HOH, or we write it as H2O. So here's an example. We have sodium hydroxide and hydrochloric acid, so we know that this is an acid. And I know we haven't talked much about bases yet, but sodium hydroxide happens to be a base, so we're going to get this hydroxide ion and this hydrogen ion, and they are going to combine to form our H2O, or water. And then our other ions, the chlorine and the sodium ion, are going to combine to form sodium chloride, or the second product. Since water is colorless and odorless, these reactions can be hard to detect because we have a liquid mixed with we have a liquid product, and then we have an aqueous product. So we need to use a pH indicator to know that water is one of our products that is present. And then we can also have reactions that form gases. And the dissociated ions combine to produce a gas. In the reaction container, bubbles form, and these bubbles are an indicator that a new gas is being produced. Gases that commonly are formed by an aqueous double replacement reaction: CO2, which is carbon dioxide, hydrogen sulfide, H2S, and hydrogen cyanide, HCN. Remember, if you have more than 2 capital letters in your formula, that means that you have a polyatomic ion. So cyanide here is a polyatomic. And in our example, here is the CO2 that is being formed. So now that we've discussed the types of reactions, we're going to go through how do we write these ionic equations that occur in the solutions. You're going to have 3 types of equations that you are writing. These are going to represent the reactions that are occurring within the solutions. And all 3 equations are going to include state of matter descriptors. So just like in our chemical reactions unit, you're going to have to label every single state of matter, both in the balance, and then when you break it into the ions, and then with the net ionic. So the first thing you need to do is you need to write and balance the chemical equation from the word equation, and you want to show all of the ions of the reactants and the products. The complete ionic equation has all of the particles, so these ions that we showed, all of the particles are shown as they exist in solution, represents the actual forms of the reactants and products. All soluble substances are represented as ions. Now, if it is insoluble and it is solid, it's not going to split into the ions. So a solid, a liquid, or a gas does not split into ions. Okay, so we have this chemical equation: 2 sodium hydroxide reacting with copper chloride, producing sodium chloride and copper hydroxide. We're going to need to put a 2 in front of sodium chloride to balance it, and that takes care of our first step. So our second step is that we need to show all of the ions. So we need to split sodium hydroxide into ions. So sodium is one of the ions that is present, and it's going to be aqueous. Now, since we have this 2 coefficient in front, there's 2 sodium hydroxides, that means there's going to be 2 sodium ions. And then hydroxide is our other ion, and again, there's going to be 2 of them. It's going to be aqueous. And then copper chloride. Remember, we can do the reverse crisscross to figure out what the charges are. Chlorine is a 1-, so that means that copper is going to be a 2+. So Cu, 2+. This is showing what is in solution. So all of these ions are aqueous. And then chlorine is a 1 minus. But remember, we have 2 chlorines in here, so it's going to be 2Cl1 minus. The subscript becomes the coefficient. And then we have 2 sodium chlorides, so we're going to have 2 sodium ions. And 2 chlorine ions. And then copper hydroxide is insoluble, so we're just going to write that formula down as it is given to us. Okay. This is our complete ionic equation with all of our ions down here. Okay. And you don't need to show the arrows to show what the ions are. I just wanted to show you where those were coming from. So the next thing that you need to do is you need to cross out the spectator ions. And think about it, if you go to a basketball game, you are a spectator at that game. So spectator ions are the ions which are unchanged when they are found both on the reactant and the product sides of the equation. So spectator ions are found the exact same on the reactant and product sides of the equations. So I just copied down the complete ionic equation that we did on the last slide. And now I want to look and see, do I have any of these ions on both sides? Well, I have 2 sodium ions in my reactants, and I also have it in my products. So I'm going to go ahead and circle those because I'm going to want to take a look at those. And then hydroxide, I don't have any in my products. Copper, I don't have any in my products. Chlorine, I have 2 of those. These have the exact same number, the exact same charge, and the exact same state of matter. So these are going to be the spectator ions. They're going to be what's unchanged. Now think about it, the basketball players are going to get sweaty, they might get dirty, they're going to be tired after the game. You as a spectator sitting in the stands, there's not a lot that has changed for you during that game. So the same thing is true for our spectator ions. Nothing has changed for them from the reactants to the product side of the equation. So now the net ionic equation, you're only going to include the particles that participated. This does not include the spectator ions. So all you're going to do is you're going to bring down what you have not canceled out in your complete ionic equation, and that is going to go in your net ionic equation. If you take a look at your net ionic equation, it should be that the ions are responsible in making your insoluble product. If not, you need to take a look back, make sure it's balanced to start with, make sure you didn't miss something that is on both sides. Okay, so we have a few practice problems to take a look at here. Our first example says that we have nitric acid combining with aqueous potassium hydroxide. So nitric acid, ic, means that it comes from an 8 acid. So nitrate is our polyatomic, and acids are always going to be aqueous. It's combined with aqueous potassium hydroxide, so KOH. Potassium is a 1+, hydroxide is a 1-. So those are our reactants. Now this occurs with a double replacement reaction. And in double replacement reactions, our cations switch places. So hydrogen and potassium are going to switch places. And so now we're going to have hydrogen with OH. That forms H2O, which is a liquid. And then potassium is going to go with nitrate, so that's going to be KNO3, and that's going to be aqueous. Remember, you can't have two aqueous products, but I have a liquid and I have aqueous, so this reaction will occur. So now I need to split it into the ions. Well, from nitric acid, I'm going to get a hydrogen ion, which is going to be aqueous, and a nitrate ion, minus, which is also aqueous, and then potassium hydroxide, so we have potassium and aqueous, and then hydroxide, and then water is going to just be copied down because it's not aqueous, so only the aqueous gets split apart. And then potassium nitrate, we're going to have K plus. And this is going to be aqueous. Okay, so now we need to go through and we need to see what's the same. Well, I don't have hydrogen ions on both sides, so I'm going to skip over that. I do have nitrate ions on both sides. And I do have potassium ions on both sides. I don't have hydroxide. These look exactly the same, so those are going to be my spectator ions that we cross out. And then my net ionic equation is going to be everything that didn't get canceled out. And there we are. We are finished. Okay, I want you to take a minute and pause the video and take a look at these net ionic equations. Do that for aqueous solutions of potassium chloride and silver nitrate. Welcome back. So we have potassium chloride, which is going to be KCl, and it is aqueous, so AQ, and it is reacting with silver nitrate, which is AgNO3, which is also aqueous. So silver and potassium are going to switch places. We're going to have silver chloride. Silver is one of the exceptions for chloride, so it is solid. And then we're going to have potassium nitrate, which is aqueous. Remember to use your solubility rules on the back of your periodic table in order to determine what the solubility of your products are. So now we need to split it into the ions for our complete ionic equation. So we have a potassium ion and a chlorine ion, and then we're going to have a silver ion. Even though silver is a transition metal, it's always going to be 1 plus. And then silver chloride is insoluble, so I'm just going to copy that down as is. And then we have a potassium ion and a nitrate ion. So now I need to look and see what is the same on both sides. Well, I have a potassium ion on both sides. Don't have chlorine. I don't have silver. But I do have nitrate. So those are going to be what gets canceled out. And my net ionic is going to be chlorine. And that is my net ionic equation. Go ahead and take a look at the practice on the next page. You need to work on that for these. Write out the balance. Make sure it's balanced. I know all the examples that we've worked on have already been balanced, but you need to double check that. Do the complete ionic and then net ionic. Stop by and ask me if you have any questions. And your homework assignment, you need to stop by and ask me about that or email me because it's not on here. So have a great day. Thanks for stopping by.